Hi, I am Dr. Syed Zahin Alam, Assistant Professor, Dayal Singh College, University of Delhi. I welcome you to this episode of UGC EPG Pathshala. In this episode, we are going to learn about plate tectonics, in which we will cover about the historical background of the plate tectonic theory, assumptions of this theory. We will also see the evidences in support of the theory. With this background, we will also discuss about what do we mean by the term plate and why plate moves. In the end, we will also discuss about the features found by the different plate boundaries. Now let us start the discussion. You must be having a fair idea about the continental drift theory given by the Alfred Lothar Wegener, who was a lecturer in meteorology and astronomy in Germany. You know from the previous module on continental drift theory that Wegener delivered a lecture on the formation of the major features of the Earth's crust. In his lecture, he suggested that continents had once been combined in the form of original single Sialic landmass and had afterward broken apart and drifted to their present positions. His theory went unnoticed by the scientific community of his day. At that time, geologists considered his theory as an impossible hypothesis. But about 60 years after the advent of continental drift theory, Jack Schmitt, an American geologist and NASA's first scientist astronaut, while flying in this space, said, "I do not grow up with the idea of drifting continents and the sea floor spreading. But I tell you, when you look at the way the pieces seem to fit together, you could almost make a believer out of anybody." During 1915 to 1960, in general, scientific community overlooked that South America and Africa appeared to fit together, which was in fact a reality. It was no less than a revolution in science and paradigm in geoscience to recognize that land under you and me is not static, rather it is moving at a rate of 2.5 to more than 15 centimeters per year. Therefore, Wegener was right that continents are moving, but since at his time there was less information about the secrets of the ocean floor, therefore Wegener was not able to convince the geologist what moved the continents. Now we know that continents are like cargo containers on a ship. That means ship transports the cargo containers, as it is evident from this animation. On the planet, this ship can be considered as a plate. Tuzo-Wilson was the first to introduce the moving plate idea in the year 1965. But his purpose was to explain the transform faults, which later became an important feature to delineate the plate boundary. Mackenzie, an English geophysicist, and his colleague Parker studied the Wilson's transform fault and moving plate idea. They identified steady direction of the plate movement by analyzing the occurrence of earthquakes around the Pacific Ocean. A Princeton geophysicist, Morgan, was also working on the same theme of plate movement. He picked up the idea of sea floor spreading, coined by Robert Dietz and explained by Harry Hess in the year 1962. This figure shows that Morgan also applied the Euler geometrical theorem to calculate the movements of plate on the Earth with reference to the axis of rotation of the plate. In this way, Morgan prepared a world map showing about 6 large and 12 small subplates. He published his findings in Journal of Geophysical Research in March 1968. Later in September 1968, I mean 5 months after the publication of Morgan's paper, 3 seismologists at Lemount, that is Brian Sachs, Jack Oliver, and Lynn Sykes, published their articles in the same journal. In that article, they concluded that seismological evidences like occurrence of shallow foci earthquakes along the transform fault and deep earthquakes along the destructive plate boundaries support the moving plate hypothesis. They also prepared a very beautiful wall-sized map showing epicenters of the earthquakes in and around the mid-ocean ridge system. It is also noteworthy that Sachs, Oliver, and Sykes were the first who proposed the term new global tectonics. The term tecton is a Greek word meaning builder. It is interesting to note that new global tectonics is now popular as plate tectonics. Now, with this historical background, let us discuss the plate tectonic theory in detail. There are a few assumptions of the plate tectonic theory. The assumption number 1 is while the new ocean crust is being generated, old crust must either be destroyed or reduced at the same rate. Therefore, the total area of the crust remains unchanged or constant. The second assumption is that sea floor spreading occurs. The last assumption is that the outermost layer of the earth, known as lithosphere, behaves as a strong, rigid substance resting on weaker region in the mantle, known as asthenosphere. The plates are continuously in motion. Now, let us see some of the evidences in support of the plate tectonic theory. We know that science requires the use of methods that are systematic, logical, and empirical. Geologists and seismologists have gathered many empirical evidences in support of the plate tectonic theory. These scientific evidences are as follows. The number 1 is the shapes match or the jigsaw fit. The second is the occurrence of the identical fossils of plants and animals. The third is the comparative stratigraphy, that is a similar sequence of rock at numerous locations. And the fourth is the ice matches or glaciers and tillite deposits. For these evidences, kindly refer the module number 9 on continental drift theory. In the present module, we will discuss the latest irrefutable evidence in support of the plate tectonic theory, that is the paleomagnetism, which is also known as fossil magnetism. The paleomagnetism is helpful to decode the magnetic reversal of rocks on both the sides of ocean ridges. The British geophysicist Frederick Wine and Matthews in the year 1963 found that same patterns of magnetic rocks exist on both the sides of mid-ocean ridges belonging to the same period. They together discovered normal and reverse polarity on the ocean floor, that is the either side of the oceanic ridges. It indicates that both sides of ridges were created during the same time period. The present figure shows that the rocks on either side of the crust of mid-oceanic ridges show remarkable similarities in terms of their period of formation, chemical compositions, and magnetic properties. Rocks closer to the mid-ocean ridges are of normal polarity and are the youngest. The age of the rocks increases as one moves away from the crust of the ocean ridges. This pattern of alternate reversal of Earth's magnetic field on the ocean floor was the most convincing evidence for the sea floor spreading hypothesis. It is also important to note that Wine and Matthews were not the first to discover the paleomagnetic phenomena. Irwin was doing PhD on the topic related to the paleomagnetism from the Cambridge University. Irwin defended his PhD thesis before the examiners and he failed. Later, after the 10 years, Cambridge University realized its mistake and awarded him PhD degree. It is also important to note that on an average, Earth's magnetic field reverses about once in every 7 lakhs years. The additional evidence of sea floor spreading came from the unexpected source, that is the petroleum exploration. Now let us discuss what do we mean by the term plate in context to the plate tectonics. The figure is showing that a tectonic plate is a gigantic, irregularly shaped, rigid slab of rock which moves slowly over the asthenosphere. Sometimes it is recognized as lithospheric plate. You already know that the middle layer mantle is separated from the crust by Moho discontinuity. The present diagram shows the thickness of a plate. It is clear that the lithosphere is carrying both granitic continental crust and basaltic oceanic crust. The diagram also exhibits that the thickness of the plate in oceanic areas is less, which may range between 5 to 100 kilometers. On the contrary, its thickness is naturally more in the continental areas. The thickness of plate in continental area is more than 200 kilometers. It is also important to note that the nature of plate also varies. For example, Pacific plate is largely an oceanic plate, and whereas the Eurasian plate may be called as continental plate. The areal size of plate can also vary from few hundred to thousands of kilometers across. For example, the Pacific and Antarctic plate are among the largest. Now, how do we know the limit of the plate, I mean edge of the plate? The edges of the plate boundary can be delineated by 3 features, that is ocean ridges, trenches and transform plate boundaries. Let us see each one separately. Ocean ridges are situated along the constructive plate margins. It represents the linear feature that exists between the 2 tectonic plates that are moving away from each other. The trenches are situated along the convergent or destructive margin. Here the oceanic lithosphere is destroyed and recycled back into the interior of the earth. In case of transform faults, there are neither construction nor destruction of the plate. The relative motion is generally parallel to the fault line, which is evident in case of San Andreas fault. With this background, let us see the distribution of major and minor plates in the world. The present map is exhibiting that the lithosphere is divided into 6 large and many smaller plates. You will notice in the map that except for the Pacific plate, the remaining major plates are named after the continents embedded in them. The Pacific plate is the largest plate and is almost oceanic in character. Many plates are comprised of both continental and oceanic crust. Let us see each one separately. The purple color on the present map is showing the size and extent of the Pacific plate. It is entirely oceanic lithosphere which covers the Pacific Ocean basin. The relative motion of this plate is northwesterly, which has resulted in the formation of subduction zones. The southern and eastern boundary of this plate is characterized by spreading boundary. In California, this plate makes an active transform fault. From the present map, it is clear that American plate covers most of the North and South American continents as well as eastern part of Russia, that is Kamchatka Peninsula. The western edge of the plate is characterized by converging boundary and the eastern boundary is situated along the western side of mid-Atlantic ridges. This map depicts Eurasian plate. It is mostly continental in nature, and this map shows that African plate is covering entire African continents surrounded by the oceanic lithosphere. From the present map, it is clear that Antarctic plate is surrounded by spreading boundary or divergent boundaries. The last one in this category of major plate is the Indo-Australian plate. The map is showing that it is more or less elongated rectangular block or rectangular plate which is mostly covered by oceanic lithosphere. This plate contains Australia, peninsular India and the New Zealand. There are also a few noteworthy minor plates. The number one in this category is the Cocos plate, which is situated between Central America and Pacific plate. Then we have Nazca plate, that is between South America and Pacific plate. Thereafter we have Arabian plate, which covers the Saudi Arabian landmass. This plate also has two transform boundaries. The fourth is the Philippine plate, which is between the Asiatic Eurasian plate and Pacific plate. The other plates are Coralline plate and Fuji plate. For detail, you can also refer the text. Now let us see the rates of movement of different plates. See, the plate movement is a very slow process and plates are moving no faster than the human fingernail grows. But by geological standards, even this movement is considered as rapid. For example, it took only 150 million years to form present-day Atlantic Ocean from only a fracture in the Pangaea. In the present map, red arrow is showing the relative speed of the different plates. The yellow color boundary is signifying the destructive plate boundaries and the red line depicts the divergent plate boundaries. From the map, it is clear that in different parts of the world, plate speed ranges from 2 to more than 15 centimeters per year. For instance, Arctic ridge has the slowest rate, that is less than 2.5 centimeters per year. On the other hand, the East Pacific rise near eastern island has the fastest movement rate, which is more than 15 centimeters per year. It is also important to note that when the new ocean crust is being created, old crust is destroyed or recycled. Therefore, the total area of the earth crust remains unchanged or constant. Now you have seen the movement of different plates. Let us see why plate moves. Within 40 years of denial of continental drift theory by contemporary geologists of Wagner's time, the main idea of horizontal movement of continent has become part of the plate tectonic theory. The technological advancement leading to the opening up of the ocean basin geology has also uncovered the mid-oceanic ridge system. The discovery of mid-oceanic ridges, transform faults, trenches and the hot spots added new dimension in the movement of plates. It is now clear that driving force behind the movement of plate is the heat. The ridge push, mantle drag, density difference and consequent slab pull are the reasons of the plate movement. Let us understand heat and mantle drag with the help of convection current mechanism. To understand the convection current mechanism, take a pan of boiling water and put a piece of cork in it. You will observe that cork on the surface of the boiling water will be pushed sideways, as it is evident from this animation. This idea was put forward by the British geologist Arthur Holmes. Geologists assume that in a similar manner, molten material is circulating deep within the earth in the asthenosphere. When hot molten rocky material floats up within the asthenosphere, it drags the plate from below, which is known as mantle drag. It then cools as it approaches the surface. As it cools, the material becomes denser and begins to sink again due to density difference, and consequently slab pull occurs in the Benioff zone. It is also clear from the figure that the hot molten magma also comes out from the weaker areas of the earth from mid-oceanic ridges, which in turn generates a pressure to push the adjoining plates. It is also important to note that plates are able to move because of the relative density of oceanic lithosphere and semi-viscous nature of the asthenosphere. You already know about the edges of the plate and plate distribution in the world. Now let us see different types of plate boundaries. Tectonic plates are constantly moving with respect to each other. They may move apart or collide together and slide or grind against each other. For each of these events, geomorphologists recognize different types of plate boundaries. Let us see each one in detail. The first one is the divergent or extensional boundary, which is also characterized as constructive margins. It is a linear feature that exists between two tectonic plates that are moving away from each other. For example, mid-Atlantic ridge separates the North and South American plates from the Eurasian and African plates. This pulling apart is causing sea floor spreading. The second is the convergent plate boundary. Here the crust is destroyed and recycled back into the interior of the earth as one plate having higher density dives under the other plate. It is also known as destructive plate boundary. In general, there are three types of convergent boundaries, that is oceanic continental convergence, oceanic convergence, and between two continental plates. The last is the parallel or transform boundaries or strike slip fault. It occurs when two tectonic plates sliding and grinding against each other along a horizontal transform fault. With this background, let us move to the last section of our discussion, that is the features formed due to different types of plate movement. Before going further, you should know the different types of plate boundaries produce different types of stresses. For example, along the divergent plate boundary, tensional stress is produced. On the other hand, along the convergent boundaries, compressional stress is generated. And in case of transform boundaries, shear stress is produced. For detail, you can also refer the module on folding and faulting. All these stresses produce different types of structural features on the surface of the earth. Let us now discuss in detail about the various features produced by the different plate boundaries. First is the divergent plate boundary features. In this category, since the stress is tensional, therefore continents split and we find rift valleys or normal faults in this case. The map shows that over the continents, the divergent zone or divergence zone is represented by East African Rift Valley. This belt extends from Ethiopia to Tanzania. And this rift valley is also the sites of volcanic activity. The volcano Kilimanjaro in Tanzania is well-known example of this belt. As Rift Valley open, water flows into the new lowlands and consequently sea is formed. The Red Sea and the Gulf of California are examples of this process. They are actually confined in larger rift valleys. Further pulling apart causes sea floor spreading. It adds new material to the oceanic plates. This process has created the longest underwater volcanic mountain range on the earth, that is the mid-oceanic ridges. The discovery of this ridge has also led to the development of sea floor spreading hypothesis, as we have already discussed. This map shows that the mid-Atlantic ridge is separated by the North and South American plate from the Eurasian and African plates. The spreading sites are the common sites of basaltic lava eruption. On the whole, sea floor spreading is basically volcanic, but it is very slow and regular process without the explosive outburst of volcanoes. Magma rises through the cracks and leaks out onto the ocean floor like a long, thin undersea volcano. As magma meets the water, it cools and solidifies, adding to the edges of the sideways moving plate. It should be noted that most of this activity is out of sight under the oceans of the world. Therefore, it is less hazardous to the pupil. It is also interesting to note that there have been many cycles of ocean creation and destruction. The periodicity of ocean formation and closing of ocean is known as Wilson cycle, which is named after the Tuzo Wilson in recognition to his research on plate tectonics, which we have already discussed. Now, let us see the convergent plate boundaries. In this category, since the stress is compressional, Therefore, the lithospheric plate is destroyed and recycled back into the interior of the earth. The location where one plate having higher density sinks under the other plate is known as subduction zone. Mountains and volcanoes are often found where plates converge. The convergence may create following situations. Number 1, compression leads to shortening of lithospheric plate. Number 2, further compression may result in thickening of the lithospheric plate. Similarly, the thickening of the plate along with the accretion of sediments may also create folding. When one plate rides over the more dense plate along a fault plane, it creates thrusting. Convergence may also create trenching. In this case, the slab of the oceanic lithosphere descends into the mantle at an angle that vary from few degrees to more than 45 degrees. The angle at which oceanic lithosphere descends into the earth depends largely on the density. At descending sites, trenches are formed. You already know that there are 3 types of convergent boundaries, that is oceanic continental convergence, oceanic convergence, and between 2 continental plates. The remarkable example of convergent boundaries are collision between the Eurasian plate and the Indian plate, which has formed Himalayas, and the subduction of Nazca plate beneath the South American plate that has formed the Andes mountain. Let us do a case study of subduction zone in the circum-Pacific belt. The zones where one plate goes under the other due to density difference are the sites of the most active and explosive volcanoes in the world. The oceanic plates having higher density is subducted under the continental crust. The subducted slab melts under the increasing pressure and temperature to produce magma, which comes out through andesitic chain of volcanoes. It should be noted that the volcanoes are mainly situated on the continental side of the trenches. The figure portrays that the so-called ring of fire or Pacific ring of fire is the collection of volcanoes bordering the Pacific Ocean. This zone is in fact a ring of subduction zone. For detail, you can also refer the module number 8, especially on volcanoes. The present map shows that the subduction of denser oceanic plate under the other plate has created long, narrow depressions with relatively steep sides in the oceans of the world. They are known as trenches. They occur either near some continental margins or are associated with some islandic arc system. The map shows that the greatest number are situated in the western part of the Pacific Ocean. Features found by different convergent plate boundaries can be summarized in this table. The table shows that the continental plate collision is characterized by mountain building, suture zone, syntaxial bend or fold with thrust fault, ophiolite shoot, remains of past volcanic activity and earthquakes. The anti-clockwise journey of India from southern hemisphere reveals that it rammed into Asia about 40 to 50 million years ago. The northward advance of India caused the rise of the Earth's tallest mountain, that is the Himalayas. In just 50 million years of the Earth's reconstructed history, peaks such as Mount Everest have risen to the height of more than 8 kilometers. The present table reveals that continent-ocean plate collision has resulted in the formation of mountain building like Andes, volcanic arc formation, andesitic lava, ophiolite and deep foci earthquakes. The ocean-ocean plate collision is characterized by trench formation, metamorphism, island arc or curved line of volcanoes and volcanic activity. Now let us discuss features found by the transform plate boundaries. In plate tectonics, a transform boundary is said to occur when tectonic plates move parallel to each other along a horizontal transform fault. They are also known as strike-slip boundary or sliding boundary. Transform boundaries are devoid of stunning landform features in comparison to convergent and divergent boundaries. The reason is that along the transform boundary, plates are merely sliding past each other and not tearing or crunching each other. The most famous transform boundary in the world is the San Andreas fault. The transform plate boundary may create arrangements like ridge transform fault, ridge trench transform fault and trench transform fault. Now let us discuss features formed by transform plate boundaries. In plate tectonics, a transform boundary is said to occur when tectonic plates are moving parallel to each other along a horizontal transform fault. They are also known as strike-slip boundary and sliding boundary. Transform boundaries are devoid of stunning landform features in comparison to convergent and divergent boundaries. The reason is that along the transform boundary, plates are merely sliding past each other and not tearing or crunching each other. The most famous transform boundary in the world is the San Andreas fault. The transform plate boundaries may create arrangements like ridge transform fault, ridge trench transform fault and trench transform fault. Now let us discuss one unique feature associated with plate tectonics, that is the hot spot. It is interesting to note that on the surface of the earth there are about 50 to 100 hot spots. These are individual sites of upwelling material arriving at the surface from interior part of the earth. The map is showing that the hot spots are located well within the tectonic plates instead of plate margins. The inset map demonstrates that the Hawaiian volcanoes are located well within the Pacific plate boundary rather than near a plate boundary. Geomorphologists say that the hot spots are the result of sublithospheric thermal anomaly. For detail, you can also refer the module number 11, especially on volcanoes. So that is all for today. I hope you have enjoyed the episode and found it useful. Thanks for visiting and watching. Goodbye.